I'm Adam Norton, the Associate Director of the Nerve Center at UMass Lowell. And I figured as part of this workshop, while we are focusing primarily on manipulation, benchmarking, and test and evaluation, I wanted to give a bit of an overview of the similar types of benchmarking and test and evaluation activities that exist for industrial robots. Because they can span many different types of systems, some of which are a little more mature in terms of standardization and adoption, and others that are a little more still living in the research world. And there's certainly some synergies between a lot of them that I think we can benefit from. So obviously there's a lot of types of different industrial robots in manufacturing environments. Those that I have on the screen here are industrial manipulators used for maybe picking tasks or grinding, composite layup. There's mobile vehicles that are used for towing payloads, maybe automating a forklift. And then systems that we would file under the human-robot interaction or human-robot collaboration category, such as those that work alongside a person, in this instance, a collaborative sanding task, or exoskeletons that are designed for industrial manufacturing environments. And regardless of the type of industrial robot that is used in manufacturing, there comes down to some kind of core metrics that in a manufacturing space, people who are looking to adopt systems and deploy them are really looking for. And those are metrics related to performance, efficiency, and productivity. There's also other metrics that are important for any of these systems related to how much they cost, their return on investment, but we're going to be focusing kind of strictly on performance evaluation for this talk. And there's a lot of different metrics that fall into each of these categories, where for the performance of a system, you may be needing to match a certain spec for certain accuracy measurements of a robot arm or certain quality of grinding you need to reach for a certain application. For efficiency, it's all related to the amount of time it takes for things to be redeployed for different tasks, or ratios of time spent in one part of the process versus another. And those two kind of combined can be used towards some productivity measures. Ultimately, throughput rates, defect rates, things that are going to affect your output. But for the type of test and evaluation methods that exist right now, some of those metrics are addressed, some of them not as much, but we want to kind of step through what each of these different efforts are and kind of see what's available there. So we're going to be talking about mobile robot navigation, the different benchmarks for robotic grasping and manipulation, and those related to HRI and exoskeletons. Not really talking about safety, because that is kind of another set of standards or evaluations that can be performed that are just kind of outside of the scope of, I think, what kind of this group might be interested in. So starting with industrial mobile robot evaluation, and I'm not going to be covering every effort that is out there, just kind of those that appear to be the most kind of salient out in the research space. So the ASTM F45 committee has been formed for maybe about 4 or 5 years at this point, and develops different test methods that are standardized for evaluating mobile robots or AGVs, meaning those that are maybe a little more automatic or automated into those that are more autonomous. And there's a couple different subcommittees that work on different types of standards in this space, such as those that are on the screen for environmental effects, docking and navigation, object detection and protection, and communication and integration. Now, each of these test methods will, or different standards will take a slightly different form, where some of them are in the form of what we call a practice, meaning something that is not necessarily a test method unto itself, but can be used for recording salient features and using them in a test method. So for example, on the top left here, this is a part of a standard for recording the environmental conditions of a test. In this screenshot, there's a very bright light that's shining at a robot, which may interfere with its sensors that it's using to navigate. So we want to record the different types of environmental conditions that exist. As part of our docking and navigation testing, we have a very simple navigation apparatus, where the robot is moving through a space, moving from point A to point B. Maybe there's different obstacles involved, but ultimately going from one point to another. In F4503, we focus on kind of the description and testing of those different types of obstacles. This is a test being performed where a small black cylinder object is placed in front of the robot that is intended to trigger its safety sensors, something that to adhere to another standard. And then in F4504, where we focus on communication and integration, there is a standard practice for interfering with the types of communication that the system might encounter. Now, what's kind of crucial to note about the way that all these different standards are designed is even though they all kind of cover different parts of the space, they are designed to work together. We've been kind of colloquially calling them building blocks. And the way this would work is in our navigation test method, we might define an area where the robot is going to navigate through, let's say this kind of T-shaped intersection here where it's moving from point A to point B. And our main metrics here are the amount of time it takes, the dimensions of the space, whether it's successful or not, kind of very kind of basic measures. If we start to apply some of our environmental condition standards on top of this, we can record where there are light sources that maybe will interfere with the robot's sensors that maybe we put in there as a challenge, or maybe they exist naturally in the environment. We want to make sure we characterize them. Using our obstacle standards, we now define where there are obstacles in the environment, which maybe will influence the path that the robot is able to take to get to point B, or maybe completely limit its path to get to point C. And maybe there are induced dropout periods where the Wi-Fi is understood to not work very well, or maybe artificially induced. And because these are formulated in this way, we can start to kind of build up our complexity into the types of testing that we want to perform. And what's also good to note about the way that these test methods are formulated is they're very much focused on receiving statistically significant results. So on the bottom left, there's a table that is used to determine the level of probability of success and confidence values associated with the number of successful repeated task repetitions. So in order to achieve 90% probability of success or 95% confidence, we would run, let's say, this environment shown on the right hand of the screen, going from point A to point B, a minimum of 29 times to say that it can fairly reliably perform with that capability in a similar type of environment. Now that's a very important aspect for the manufacturing world, as opposed to maybe the amount of testing we might do for a research paper or elsewhere, where we always want to achieve statistical significance, but maybe we can live with a lower number of repetitions. Whereas in the manufacturing space, this 29 repetitions, this is really the minimum. Most places that make these types of vehicles, they're going to be testing in the hundreds of times and kind of increasing their their reliability, because they don't want any sort of failure while you're out in the environment. Now, moving to manipulation, there's not necessarily a fully realized standards committees similar to, say, ASTM just yet. But there is the IEEE Robotic Hand and Grasping Manipulation Group, which some of our organizers are very active in. A new IEEE standards activity, which is just getting spun up, where hopefully some of our standard metrics and test methods will be more widely proliferated throughout the industry. And then, while not strictly focused on manipulation, the ASTM E57 Committee on 3D Imaging Systems has been kind of reinvigorated into focusing on perception, more specifically tuned to robot assembly applications. So it has a lot of kind of overlap in the way that we would evaluate some of those manipulators. Now, on the side of robot manipulation, there's a very wide kind of gamut of the types of tests that have been defined, or those that are at least kind of used out in the research space. Down from end effector characterization, this here is 2 artifacts that are out of NIST for evaluating grasp and finger strength, kind of very core elemental capabilities of different end effectors. Then kind of moving further along the complexity scale is test methods for grasping or picking. On the bottom left here is the ACRV picking benchmark, which is basically a standardized version of what's been used in the Amazon picking challenge. where a series of standardized objects are picked out of a shelf. And some of those objects may be the YCB object set, another very common set of standard objects that are used for manipulation research. And then furthest up into at least the existing kind of complexity level for test and evaluation resources are the disassembly task boards, those that are very largely the subject of today's workshop. And Kenny touched on kind of the different variations that exist with each of these boards. Now, given that wide array that are really focused on kind of grasping and assembly and manipulation, some of them we can actually start to use to look at the perception and adaptation capabilities of robotic manipulators. So for example, when these have been, the assembly task boards have been used in competitions like Kenny was mentioning, there are some mechanisms that are used to try to force the ability for perception and adaptation capabilities. For example, training the teams on one board, having one board that's made available to them ahead of time, and deploying a different board at the competition, where the same tasks are used, but they're laid out a little differently. If anybody has their microphone on, I'll ask you to please mute. Or changing the orientation of it, requiring there be some perception to say you might know the relative location of these tasks to one another, but their global reference frame is going to be off a little bit. Now, while we're starting to see these go out into the more kind of standardized and industry space, it's more so on the elemental grasping artifacts are starting to be used in some ISO standards for evaluating grippers. And hopefully this new IEEE standards activity will take some more of our task-based manipulation test methods and start, kind of adopting them and proliferating them more as a standard. But on top of this, there's a lot of many other type of benchmarking tools in development for in-hand manipulation, cloth manipulation. It's a very, very active research area at the moment. And I think that's because of kind of the versatility of those types of systems. It can, get a lot of activity around it. Now, lastly, I'm just very briefly going to go over some of the resources that are available for HRI evaluation. HRI evaluation and manufacturing spaces can span many different tools and different measures. So I'm not going to spend too much time on them. I'm going to more focus on the exoskeleton side. But I did want to leave, if anyone is interested in learning more about HRI evaluation in manufacturing environments, there's a great paper that was just recently published that kind of catalogs a lot of the different metrics and measures for HRI in manufacturing spaces. Because on the exoskeleton side, it's similar to F45, where we have a standards committee that is focused on testing and evaluation of exoskeletons and exosuits. And their test methods will actually function somewhat similarly, where maybe we have a test method for load handling happening in some standard apparatus, a practice for recording the different environmental conditions under which that test is performed, and a practice for defining certain mobility aspects of those types of test environments. And they're leaning towards that same kind of structure, where they're put together kind of like building blocks, where you can start to combine different elements of different standards to make more complex and comprehensive testing. So kind of looking at this at a larger view, there's various different test method domains, and some are more mature, some are living more in the research space. And some of this comes down to either the maturity of the technology or how broad or narrow some of these research areas are. So in mobile robot navigation, ultimately, there's probably a limited number of unique tasks that a mobile robot system on its own can perform. And they all really come down to moving from point A to point B, maybe with more accuracy, maybe moving within obstructions, but it does have a fairly narrow kind of space in that regard. So the fact that they are standardized and proliferated into industry, it makes sense. It's easier to kind of build some consensus. On robotic manipulation, there's a very wide span of the different ways you can evaluate those types of systems, from our lowest tier of end effector characterization all the way up to perception-based assembly. But there is a lot of commonality in the way that some of these testings are performed due to the availability of different benchmarking resources. And very similarly for HRI, kind of exists somewhere in the middle of the previous two, where there's still challenges associated with getting statistical significance in some of our data, because anything that involves human inherently becomes a much more higher dimensional problem. And while there are a lot of accepted tools, not as many manufacturing specific standardized considerations for evaluating HRI. And there's the exoskeleton community that I think is kind of gleaning some of the lessons learned from the other spaces. So it kind of leaves these series of questions. Are the current test methods that we have or that are currently being developed, are they sufficient? Can we go back to those core metrics that are relevant for manufacturing? And can we actually derive some of those measures from those test methods? Certainly you can evaluate grasping, you can evaluate assembly, but there's not really a standardized way to look at these more very manufacturing focused tasks like grinding, polishing, welding, composite layup, without doing highly specific experiments. Efficiency certainly is in there. Timing is a core metric for most of these test methods. And productivity is something that could be derived given that you test in a way that is looking at, let's say, an entire suite of repetitions as opposed to single ones. But more importantly, are we actually evaluating the advantages of using robots in manufacturing? They are made to be robust, adaptable, generalizable, improving and learning over time. And I think to date, there has not been as much focus in those areas, but it's encouraging to know that there are some new efforts that are starting to look on these aspects. So ultimately, there is more manufacturing test method focus that is needed. And I think the assembly task board that we're kind of largely talking about today is starting to lean towards that direction. But there's certainly other areas where we can take our various robot capabilities, kind of elevate them into what is needed for them to be a little more manufacturing focused. And that is my talk. Thank you very much. Anybody have any questions?
Yeah, thanks for the talk, Adam. I had a question. So you were focusing on, and rightfully so, modularity in assembling these tests together. Is there a standard way of, I guess, dealing with or expressing how one task might slow down or impede or hinder the next one in line?
I think that's a good way to think about it. It's certainly in terms of thinking it more as a process, where right now a lot of our evaluations are largely for kind of single tasks, single capabilities, not looking at, let's say, the performance of tasks in tandem, or doing things more as kind of a process or workflow. So I think some of that is not really being considered just yet, but given that we are formulating our tests to function as kind of like building blocks, I think that is one avenue we can start to explore.